Now that we've found our three local stiffness matrices, it's time to assemble our global stiffness matrix. Now, in our case, our system has 4 nodes, and at each node, I'm looking for both the displacement in the x direction and the displacement in the y direction. So in fact, before I apply boundary conditions, I have 8 unknowns. So my system, my global stiffness matrix, is going to be a system that's an 8x8 matrix. Now, in a last lecture, I found the form of our 3 local stiffness matrices. And I just want to remind you, it's always a good idea when you do this step to remind yourself what nodes were element number 1, element number 2, and element number 3 connect to. And the best way to do that is to notate in the corners of your matrices the fact that this first column refers to x of node 1. This refers to the y of node 1, x of node 2, y of node 2. Remember the structure of our truss. We have 3 bars, which we called element number 1, element number 2, and element number 3. We called this node node 1. This was node 2, node 3, and node 4. So element number 1 connects node 1 to node 2. Element number 2 connects node 1 to node 3. And element number 3 connects node 1 to node 4. Now, I went ahead and kind of wrote out our grand global stiffness matrix, or at least the shell of it, to save us some time. But notice I've done the same thing for my global stiffness matrix. The idea is that everything that's in a particular row and a particular row and a particular column, if it's the x1 column and the x1 row, it'll be put into the x1 column and the x1 row here. Now, to make things a little bit easier on us, because this is a fairly straightforward problem, I'm going to go ahead and I'm going to give some new notation. I'm going to say that 50,000, which is the same as, 500,000, which is the same as 5e5, is this equal to kappa superscript 1. And that way, I can basically say everything in this matrix is kappa superscript 1, negative kappa superscript 1, or 0. Same here. Everything in this matrix is kappa superscript 2, 0, or negative kappa superscript 2. And everything here is kappa superscript 3, 0, or negative kappa superscript 3. Now, on another problem, on a more complex problem where we didn't have this nice 0, 45, and 90-degree angle, we might not be able to do this, and we need to find superscripts and subscripts for each element inside these matrices. I'll add that complication later as we do some more problems. But for now, we can rest assured that everything in this matrix is either positive kappa 1, negative kappa 1, or 0, and so forth. All right? So let's go ahead and start filling in our global stiffness matrix. Now, for the first matrix, our first local stiffness matrix, everything's fairly straightforward because it has the same structure, everything column in. So we can just take this matrix and we can just plop it in to the first 4 rows, first 4 columns, and the first 4 rows. And what we will get is there's a 0 here, so we'll get 0, 0, 0, 0, because this entire row is 0. Here we'll get 0. That 1 is going to become a kappa superscript 1, kappa 1, 0, negative kappa superscript 1. It looks like we'll have all zeros along here, and the last row will give us 0, negative kappa 1, 0, kappa 1. Moving on to the next local matrix, now here, every element is either going to be a kappa 2, 0, or negative kappa 2. If I look at, here I have column 1, x1, row x1. What I'm going to get is in these 4 elements, I will get plus kappa 2 plus kappa 2 plus kappa 2 plus kappa 2. I have these all negative kappa 2s in this quadrant here of this matrix. This applies to the third x3 and y3, but it applies to the column, but the x1, y1 rows. So here I will get negative kappa 2, negative kappa 2, negative kappa 2, negative kappa 2. Likewise, here on the first 2 columns, the x1 and the y1 column, but the x3, y3 rows, I will also get y3. I will get negative kappa 2, negative kappa 2, negative kappa 2, negative kappa 2. And finally, in this quadrant right here, I have x3 and y3 column, x3, y3 rows. These 4.5s will all actually be positive kappa 2s. I'll get kappa 2, kappa 2, kappa 2, kappa 2. And that should complete out the second local stiffness matrix. I'm ready to move on to the final stiffness matrix for element number 3, applying to this bar, connecting node 1 to node 4. Again, in this quadrant here, I have x1, y1 row, x1 and y1, I'm sorry, x1, y1 column, x1, y1 row. These will all be, looks like I only have a plus kappa 3. This will be a plus 0, a plus 0, a plus 0. Here I have the fourth x4, y4 column, x1, y1 rows. So this quadrant, I'll have a negative kappa 3, 0, 0, 0. Here from x4, y4, x4, y4, the only thing here is a negative 1. That'll be negative kappa 3, negative kappa 3. Looks like everything else will be zeros. And then finally, here in columns x4, y4, row x4, y4, I will have a kappa 3, 0, 0. I'm done filling in all the information I got from the 3 local stiffness matrices. Anywhere I don't have any values, these will all be zeros. Okay? You'll note again the structure, if I did this correctly, which it looks like I did, is symmetric. Now I've gone ahead, and on the next slide, we will transfer to the actual numeric values. Remember, kappa 1 equals 500,000. Kappa 2 equals 500,000 divided by 2 over the square root of 2. Kappa 3 equals 500,000. So numerically, this becomes a fully numeric matrix. All right, so now we've found our global stiffness matrix. We'll take this global stiffness matrix, apply our boundary conditions in the next video.